Okay, last step in our journey through vectors is projectile motion. So what is projectile motion? Projectile motion is, for example, let's say you're moving, like this person is on skates, going in this direction. If you drop a ball while you're moving, the ball will travel with you, bounce right back up, and come to your hand. Okay, so what we see is we see the ball taking a path that is curved. Why this is important is because, and this is what's important, the independence of horizontal and vertical motions. And that's what we see with projectile motion. So, projectile, object that is launched and then follows a path determined solely by gravity. So the only thing that's changing this path is gravity. Now, here's the other thing, is that the path is parabolic, okay? Because we ignore air resistance and gravity, g, acceleration due to gravity, g, negative 9.8, is constant, and it's always directed downward. So the parabola we see is produced by the combined effects of the horizontal and vertical motions, or vectors, acting independently, and then we put them together to get the actual velocity. Okay, independence of motion means that the position-time equation that we talk about, we could do for both, right? Here are some things that we always keep track of, okay? So this is the path of a projectile. Acceleration in the x is 0, acceleration in the y is negative 9.81. Always true when we talk about projectile motion. So when we look at equations, here's the x equation for position time. Notice there's no acceleration in it because it's 0. And then for the y, we've already made it negative, and we've incorporated g as the acceleration. So on Earth, 9.8, but the negative's already put in there. Initial and final positions are still there, and initial and final velocity are still there. Okay. So here's an example. So we got a person skateboarding with a speed of 1.30 meters per second, releases a ball from a height of 1.25 meters above the ground, as we saw in the previous figure. Knowing our initial positions, we want to find our final positions. Knowing this time, or these two different times, and then g, of course, 9.8. Okay, so let's look at x first. X initial plus v initial in the x multiplied by time. Again, acceleration 0, so I use this equation. My initial position in the x is 0. My initial velocity, so we're going this fast and we're dropping it straight down, okay? Which means my initial velocity in the x is going to be this 1.30. And I multiply it by the time of 0.250. And then the rest is just punching numbers in and doing math. And when we do that, 1.3 times 0.25, 0, we should get an answer of 0.325 meters. And that's at a quarter of a second. For our y final, it should be a y, should be y initial plus initial velocity in the y times t. That should be minus, 1/2 g t squared. So our y final is going to be 1.25 plus our initial y. Since we're traveling this direction, our initial y will be 0 when we drop horizontally, minus 1/2 9.8 0.25 squared. So we do all this math, we're going to get a negative number here, so that's going to change our answer a little bit. That means we're going to go down. Our final y should be 0.943 meters. So that's how we use those equations. And because the negative's already in there in the equation, obviously we don't have to make 9.8 negative. We're assuming that since we're going down. To find your answer for 0.5 seconds, just substitute that in for t in each of those instances. next thing we're looking at is throwing a baseball. Okay, so you're on the roof of a building and you're throwing a baseball to a friend. Okay, you're throwing it outward. So we want to know, as we throw it out to our friend down here, it's going to take this path, right? The parabolic path. After 1 second, how fast is it moving in the x and in the y? So how fast is it moving in the x? And how fast is it moving in the y? So we want to think about equations that we could use, right? Equations that we could use when we talk about velocity time, all right? And here's what it is. Velocity in the x initial will equal velocity final initial. Always true. So whatever our initial velocity in the x is here will be the same as this. That's easy enough. In the y, the equation should look similar. Velocity final in the y will equal velocity initial in the y. And we're going to subtract from that g times time. So we'll substitute in. So what's our initial velocity? Well, our initial velocity is 12.0 meters per second. So that's going to be our final velocity. So our final velocity in the x is 12.0 meters per second. In the y, since we're shooting straight out this way, our initial velocity in the y will be 0. So final velocity in the y is equal to 0 minus 9.8 multiplied by 1. So our final y velocity should be negative 9.8 meters per second. And it's going down negative 9.8 meters per second. So this is another equation that you can use. Okay, so we have two people overhanging the lake in the pictures here. Diver 1 is dropping straight down. Diver 2 is taking an angle. Is the speed of diver 2, okay, greater than, less than, or equal to that of diver 1? Well, diver 1 is dropping straight down. So diver 1 has no horizontal velocity, right? So we look at the velocity vectors affecting diver 1, and all you see is 1 going down. When we talk about the person jumping out, their y is going to be the same. But since they have a horizontal velocity, they're going to have this. If we add our vectors, y and then x, we're going to have a hypotenuse for our final velocity. This final velocity, okay, of 2, will always be greater than that of 1. So if you want to hit, if you're jumping off a diving board or a cliff or whatever, and you want to have a greater velocity when you land, you want to give yourself a horizontal velocity to get that done, so that your combined vector, your resultant, will be greater. Okay, so angle launches of projectile motion. This is what you're going to see with your trebuchets, and so we want to take a look at angle launch, and I'll give you a couple equations that will help. So here's what we know from before when we talked about using vectors and sine and cosine to solve problems. We can break an initial velocity, if we know the angle of launch, into x and y components. And we can use cosine for our x component and sine for our y component. So we're going to substitute those into position time equations. And here's what we get. We get this equation. Final position in the x is equal to xi plus vi cosine theta times t. And then we just substitute our initial velocity here, vi sine theta times t, for our y. So we can use these two equations easily to find distance. Velocity time equations. Our final y velocity is going to be initial velocity times cosine theta, and our final y velocity is going to be vi sine theta minus gt. These are equations when we're at an angle. Write these down, and you can use these at any time to solve. So here's an example. We got a golf example. We're hitting from the rough. Golfer sends the ball over a 3-meter high tree that is 14 meters away. The ball lands on the green. Of course, I'm the one hitting the ball here. At the same level which it was struck, after traveling a horizontal distance of 17.8 meters. So here's going to be our 17.8 where it hits the ground. If the ball left the club at an angle of 54 degree loft club, above the horizontal line of the green 2.24 seconds later, what was its initial speed? It passes directly over the tree, so here, right, it is at 1.76 seconds, it says. And how high was the ball at this time? So we have a couple things to look at. All right. we want to find what was its initial speed when it left the club to land where it landed, and then we also want to see how high it was how high it was when it went over the tree. So let's take a look at A first and see what we're going to use to solve this. Okay, so if I look at A and I know my angle, and I can do some things with this, and I know my horizontal distance, and so I know my horizontal distance is 17.8. All right, I know my time for the total trip was 2.24 seconds. All right, and so knowing that information, and I know my angle, is 54 degrees, I can find an equation that'll work. And so first off, I want to see my initial velocity. So I can use this one, xf, xi, all right, plus, and this is one of the equations I just showed you, vi cosine theta times t. So xf is the total distance traveled in the horizontal, which in this case is 14 meters. I'm sorry, well, not 14, 17.8. My initial position we're going to say is 0, right, because that's where I'm at 0. I don't know VI, okay, but I know cosine of 54 is my angle, and my time is 2.24. And I want to solve for VI. So what I would do is I would divide both sides by 2.24 and divide by cosine of 54, and I would get VI. And when I get VI, what I should get is 13.5 meters per second. And that's the initial velocity resultant, okay? Now, for B, I want to find how high the ball was at the time it went over the tree. So that's my Y, okay, my Y distance. My Y final, is going to be equal to my Y initial plus VI sine theta t minus 1/2 GT squared. So my Y position final I don't know. Initially it's going to be 0 because we're starting at the origin. All right. My initial velocity is here. It's 13.5. I got this from that answer. I'm going to multiply that by the sine of 54 minus 1/2 9.8, and I know it took 1.76 seconds. 1.76 seconds squared. And again, solving for YF, and you can put all this into your calculator, but YF is going to equal 4.03 meters. So that's how high it was when it got there. Okay? And the tree is 3 meters high, so we definitely cleared it, which is kind of important when you're playing that shot in golf. You and a friend have initial speed of 10 meters per second. Your friend catches the ball at time t at the same level from which you threw it. Which of the plots best the speed of the ball as a function of time? So your friend catches the ball at the time at the same level from which you threw it. So the speed of the ball is going to land, it's going to take off. Is the ball going to speed up or slow down as it takes off? Well, it's going to slow down. So the speed is going to decrease. Then it gets to it. So I'm sure that this is you and your friend. Here's you. Here's your friend. The ball leaves. It slows down till it gets to this point at the very top. Velocity 0. Then it comes back down to your friend. So the speed's going to decrease, then increase back. So 2 is the best answer here. Another equation that is useful is the range equation, and you can see this here. When you get ready to do a problem with range, you should see me, and I will show you how to use this. It's not necessarily the easiest equation to use, but it will make your life easier. And then those that meet with me, we can talk about different equations that you need to solve for. Everyday objects. Ideal projectile. What's your ideal angle? When you launch using your trebuchet, the ideal launch angle without air resistance is 45 degrees. Now with air resistance, you might find a variance in there. A little bit above or below 45 might be what you need. But without air resistance, 45 is by far the ideal projectile angle. And you can see with air resistance, 45 is still best. It's just not the overall best, or not as good as before.